All right, welcome back to our last lesson in Unit 6 of Algebra 2. Now, Unit 6 has been all about quadratic functions, and we've looked at solving equations, we've looked at graphing them, we've looked at zeros, we've even looked at inequalities. So we're going to finish off this discussion by problem solving. Now, I know problem solving, word problems in general, can cause people a lot of anxiety, but we're going to try to keep that to a minimum by reminding you that while there are many applications to quadratic functions, the only ones that we're going to be studying here are the ones that I consider to be the most classic, the ones that the most universities would have expected you to have seen, the ones that are most common in textbooks. So I'm not going to be throwing anything at you that isn't one of the problems that you'll see in these problems, and the other problems will be just variations. So I'm trying to give these questions some titles and some ways for you to think about, so that whenever you come across a new word problem, you can think, well, isn't this really just kind of like this other problem, but maybe with a slightly different object? Let's take a look. By object, I mean for the first problem, we're talking about a football, but it could be the same problem with a baseball or golf ball or anything like that. So just learn this problem. All right, Hugh Stone kicks a football off the ground with an upward velocity of 19.6 meters per second. How high does the football reach off the ground? For how many seconds is the football in the air? So we have two questions. So I'm going to call this part A, and I'll call the other one part B. Okay, so let's start with part A. We are going to be determining how high does it reach off the ground. Well, in order to do that, we'll need an equation, and which we have right here. H of t, height as a function of time since the football was kicked, is given by this equation here, where it's negative the rate of gravity divided by 2 times time squared plus v with that little circle at the bottom. That's pronounced v naught, which I think is spelled N-A-U-G-H-T. All right. So some people will use VI for V initial, meaning at the start. But whatever it is, it just means the velocity the football is kicked with. Because of air and gravity and all that stuff, the football does not maintain a constant speed. It will slow down as it goes up in the air. So we need to start with V naught being the initial velocity, just the speed at which it was kicked. Okay? And then finally we have h naught, which is the initial height, because just like the velocity, as the ball is moving up and down, clearly the height is changing as well. So h naught means just the height when it's kicked. H is the height at any moment over time. All right, so we'll start by filling in the different parameters of our equation. So negative g over 2, where gravity is approximately 9.8 meters per second per second. Don't be confused by the per second. That's because it's an acceleration. It means that it's speeding up 9.8 meters per second each second. So each time the velocity is getting faster and faster. So we'll divide that by 2. So that makes it negative 4.9, because it's g over 2 t squared plus v naught, the initial velocity. Well, we were told it was kicked upwards at 19.6. So 19.6 times t. And we were told it was kicked off the ground. If it was kicked maybe off of a tee or something that's higher up off the ground, then we might have something here. But instead, our h naught is just 0. Which, of course, I don't need to write, but I just wanted to show you where I got each one of those three things. So I'll take it off there. So the first question asks, how high does the football reach off the ground? Well, let's remember our key points in a parabola. That's the vertex and the zeros. Is this question asking about a vertex or a zero? Well, if we graph this equation, it's going to be a parabola that is going to go up and down over time, where this is time in seconds and this is the height. This point right here will be the time of the highest point, and this would be the height of the highest point. So let's go right to it, and let's pull out a graphing calculator and let's graph this together. So I'll be using Desmos again. You can use whichever graphing calculator you like. And I think you can actually say h of t if you really want to keep it the same. And it should graph it. Okay, so there it is. Now the window's a little bit unusual here, but maybe you want to go to this settings and maybe change this window. You can see the ball goes up and down very quickly. So I'm going to make this go from like -3 to +6. Okay. All right, that point right there is my highest point at 2, 19.6. So it turns out that that value there, that highest point, is actually equal to that initial velocity in this case of 19.6. So the max height is equal to 19.6. Now, how would we find that value if we didn't want to have to graph it on a graphing calculator? Well, since this is a vertex, we have a formula for the vertex. The vertex occurs at an x value, or in this case a t value, at -b divided by 2a. So I would do -19.6 divided by -2 times a, which in this case is 9.8. Which is kind of an interesting result. So you can see that if something is launched from the ground, the time that it will reach the maximum height will always be equal to the velocity it was kicked at divided by gravity, which is kind of a cool result, I think. And 19.6 divided by 9.8 is 2. Now, to find that height, I simply plug it in. So I would find h of 2 by replacing the t with a 2, and we already know that that worked out to be 19.6. But let's go ahead and find out h of 2. We could also just type it in directly, -4.9 times 2 squared plus 19.6 times 2. All right, so that's the answer. This is how high does a football reach off the ground? 19.6 meters, which, if I'm not mistaken, is quite tall. But I'm just kind of made up these numbers, so pardon me if they're not realistic for an actual football. But I don't know, maybe that's realistic. All right, now we got to do part B. So part B is about how far did it go? Well, we know it started here, right? And then it landed over here. Now, that's not a distance, because this isn't distance. This is time. I said how far. I should have said how long was it in the air. So how long was it in the air? Well, we see that right here with that value there at 4.0. So we would say 4 seconds. Again, I want to ask you, how would you solve that without just using a graphing calculator? Well, the way we would do that is we'd simply solve using the quadratic formula or factoring. So we would simply solve this equation to get the answer. And I'll leave you to do that, but the answers are 0 and 4. And so 0 was one time. There's always going to be 2 of them. That's the time when we kicked it. So I don't want that. I want 4. 4 seconds. Okay. Let's take a look at the next one. Okay, the path in the xy plane of a projectile launched from a height of y0 with a velocity v at an angle of 45 degrees is described by this quadratic equation here. So it turns out that if you launch something at a 45-degree angle, then you end up giving an equal amount of its velocity towards going up as you do having it go out. And so it makes for a relatively simple equation. When you start using different angles than 45-degree angles or 90-degree angles or things like that, the numbers get a little yuckier. But this one's pretty approachable, so let's give it a try. So if a potato gun, which is literally what it sounds like, a gun that shoots a potato, launches a potato from a height of 7 feet at a 45-degree angle with a velocity of 70 feet per second, what is the maximum height of the projectile, and how far does it travel? So this is a different situation than the last problem, because now we're literally looking at x as a horizontal distance from where the potato is fired, and y as a vertical height. And this potato looks like it's actually going to start at a height of 7 feet. So it's going to go something like this. It's going to reach a maximum height, which is a y coordinate, and then it will reach a maximum distance, which will be an x coordinate. So we're just going to use the equation. Gravity, we're going to be using gravity in feet per second squared, so a little different number here. Oops, sorry for that typo. Either this needs to be negative or that needs to be negative, but not both. So it should be 32. So it should be a negative 32 divided by velocity of what it was launched at, 70 squared, x squared plus x plus the initial height. So that's a pretty yucky number, isn't it? Negative 32 over 70 squared. Negative 0.00653, approximately. But that's it. Let's go ahead and graph it. And these numbers aren't so pretty, so I'm just going to rely entirely on the graphing calculator. And we'll take a look at that. And you can see we really need to spread out this time. I'm going to go back to a normal zoom. I'm just scrolling out till I see everything that I need to see. And there we go. You can see there's our height of 7. Looks like we got a max height of 45.285. So we have max height equal to 48.285 feet. And we're going to have a max distance. How far can it go? And I'm saying max, in fact, that is the furthest you will fire something is at a 45-degree angle, barring wind resistance, anything like that. But typically 45-degree angle is that perfect in between. So then we have 159.846. So 159.846 feet. And there it is. That's all there is to that one. So that's a pretty good practical application to a quadratic equation, right? Seeing how far maximum height you can, the maximum distance you can fire something at will be at a 45-degree angle. So you can use that to find out. All right, let's take a look at a business problem. After extensive market research, Ethan Mapai finds that he will sell 5 additional of his mini pecan pies at the market for every 5-cent decrease in price. At last month's farmer's market, Ethan sold 50 pies for $6 each. What price should Ethan sell his pies for at the next farmer's market to maximize his revenue? Okay, so revenue is price times quantity. You might think of it kind of like profit, but it's really not, because we're not taking into account how much Ethan is going to spend on what is he making, pecan pies, or whatever ingredients that he's making here, the flour and the sugar and all that. So this is just how much money he makes from selling it, and we're trying to maximize our revenue at this time. So to maximize revenue, remember that revenue is equal to price times quantity. Well, his revenue is going to be the price that he sells them at, which was $6, right? He sells them for $6. And leave a little blank on that, though, okay? So we're going to look at that come back in just a second. And the quantity he sold was 50. But he found out something. He found out that he will sell 5 additional for every time he drops the price by 5 cents. So every time he drops the price by 5 cents, he'll get an additional 5 pies. So I'll say 5x. And for every price change, he's going to lower it by 5 cents. So we see that for every price change X, the price of the pie goes down by 5 cents and the number of pies goes up by 5. If you prefer to let X be quite literally a 1 cent price drop, then you need to do some kind of analysis there to get to change the 5 into like a percent change. But we want to look at this in terms of how many times does he do a 5 cent price increment decrease, because that's what our research shows. So we're letting X be the number of 5 cent decrease in price. Okay? So that's our equation right there. All we need to do is graph that and find what's going to give us the maximum revenue. So let's go right to that. So again, starting with a $6 base price, which goes down, so minus 5 cents for every price change X, we're going to multiply that by 50 plus 5 additional pies for every price change. And you can see that right there at 55, we're at 1,056 and 25 cents. So 55 price changes, right? Well, what price does that correspond to? Well, that corresponds to 6 minus 0.05 times 55. Which is $3.25. So $3.25 is that perfect price to get the most money per pie. You might think, well, what happens if you were to decrease the price even more? Decrease it down to $3.20. Well, if he decreases it down to $3.20 by going with 56, what ends up happening is that, yes, Ethan will sell more pies. We know he'll sell 50 more pies. But because of the decrease in price, he's getting so much less per pie over all of them that it ends up not to be worth it. All right, let's try another one. The largest pin possible. Anne Malcaire has a nice country home for raising goats. She has 200 feet of fencing and wants to build a rectangular pen for her goats. On one side of the pen will be one side of the pen will be against her rather large house, so she only needs enough fencing for 3 of the sides of the rectangular pen. What is the maximum amount of area she can enclose, and what dimensions should she use? Now, I doubt 200 feet of fencing is an adequate amount of space for goats, but I didn't want the numbers to be too big, so, forgive me on that. So here we go. We're going to put these goats inside this pin here, right? All the goats are going to go in here. But it's an important issue with this pin is that we're actually only building 3 sides. So I'm going to call this my length, and I'm going to call this my width, and you can see I have another length here. So we have 200 feet of fencing, and we have length plus width has to equal 200. If I solve that for width, I get 200 minus 2L. Hopefully you see how I did that. I combined the 2 L's and then subtracted them over the other side. The area of this pin will be the length of the pin times the width. So my area is length times 200 minus 2L when I replace width with what width is equal to. I can then graph this to find the length that corresponds with the largest A, the area. So I'll just use X. And I'll go back to I'll start with my standard zoom here. Start zooming out. Wow, this is a rather tall yet narrow thing. So I think it might be helpful if we just decrease this X down here to, well, I think anywhere from 0. We could have 0 to maybe, 200 might be a better description of what's happening. Okay, there we go. since we only had 200 feet of fencing anyway. So it looks like if we make our width 50, we'll get 5,000 square feet in area, which is the max. So we need to, I'm sorry, that's the length. We'll make the length 50. Now remember, the width is 200 minus 2 times the length, so my width must be 200 minus 2 times 50, so 200 minus 100 is 100. So it looks like this width, since we only need one of them, we should make that width twice what we have the length. That's dimensions that we should use. And then what area did we get? Do you remember? Because I think it was like 5,000. Now 5,000, that's probably not enough for a goat, but you get the idea. Maybe make these meters, and then it's definitely enough. All right. How about this one? We have the largest adjacent pins possible. A little different situation. So Horst Lover wants to build 2 fenced-in pins for his horses and cows. He has 400 feet of fencing material. Again, probably not enough, right? He plans to make the 2 pins congruent and adjacent rectangles. So the pins will share a common wall as shown in the diagram. All right, so this is another situation where we're going to be building this fencing all the way around, but what makes this a slightly different problem is that we have this 1, 2, 3 of these widths. So if I call this length for the entire length of it, right? And then I've got a width and a width and a width. I could also call this length and length and say there's 2 lengths, but this is what I'm going to do. Call this one big length here. So we know that we have 2 lengths plus, oops, said length, but wrote W. 2 lengths plus 3 W's is equal to 400 feet. And I'm going to solve that for L. I think that'll be easier. Dividing both sides by 2 gives me, and I'll just go ahead and distribute it here. And then 400 divided by 2 is 200. Now the area, we know, area will be length times width. So my area is the length times the width. So you see I replaced L with that expression involving W. So we're going to solve this for the optimal width so that we get the most area combined between the two. So that's a negative 3 over 2x plus 200. And then I think that's just times x. All right, so you can see here that maximum is at 66.667. That's the perfect width and the perfect area is 6,666.667 square feet. Okay? Now, it looks like I'm missing the question part of this. I need to fix that, but that's okay. So there we have it. 66.667 feet is the perfect width. And the length that goes with that, I will again utilize my calculator here. That's a negative 3 over 2 times 66.6667 plus 200. Looks like that number is 100. So we're going to do a length of 100. Okay? All right, and there we have it. All right, I got a couple of practice problems for you to do. First, we're going to use looks like a revenue problem, right? Go ahead and give this one a try. Read it carefully. Sometimes we talk about the price going up. Sometimes we talk about the price going down. Other times we talk about the number of sales going up or the number of sales going down. So just keep track of it. And remember to declare a variable x, make an variable x that is equal to the number of price changes. In this case, it's a $25 price change. All right, give it a try. Pause the video, and then we'll go over it. All right, let's see how you did. Remember that revenue is the price you sell something at times how many you sell them. Well, we learned that last year they sold 300 of these at a price of $4,250. So originally we were doing $4,250, and we're going to change that, okay, times a quantity. Well, the quantity they sold was 300, but we're going to change that as well. We found that we're going to sell 5 fewer golf courses a year for every $25 increase. This is the number of $25 increases. So we're going to take the price and we're going to increase it by $25. Now you increase this by $25. If you think about it, making it $4,275, most people are going to be like, oh, okay, fine. It's $25 more than I wanted to spend, but I'll still spend it. But there's going to be a few people who might say, whoops, no, I'm not going to buy that. And it turns out there were 5 people that were priced out of the market. For every time you increase it by $25, there's going to be 5 fewer people that are going to buy it. Okay. Let's see which one of those values is associated with the best outcome for us. So 4250 plus 25x times 300 minus 5x. All right, so I'm going to go back to this kind of standard looking thing. I'm not sure what settings I should really use here. Let's talk about the y-axis. That's going to be revenue. Now, if you take 4,250 and multiply it by 100, it'd be 42,000. So this is going to be a pretty big number. I'm going to make this like $80,000. Okay, and then for the x-axis, I'm going to make this maybe go from like 0 to, I don't know, maybe like, well, not 0, because we could actually do some negative numbers here. I'll do like negative 10 to maybe like 20. Let's see if that doesn't give us a good value. Wait, I'm still not getting it. What is going on? Let me do some trick. 4.2. The original height was at that. Oh, I'm nowhere close. I am nowhere close. I need to add another 0 to this puppy. Because I need to go 1275. That's just barely going to get there. Let's make it like 2. All right, there we go. Okay, so you can see that, in fact, in this situation, it looks like they're overpriced, right? So it turns out that negative 55 is the way to go. So what would that turn out to be? 4250 plus 25 times a negative 55. Wow, they are really overpriced. So we need to change the price. We need to change the price to $2,875. I get that because the vertex, let me draw that over here. Because that vertex right here, this maximum value is at negative 55 right here. So that's saying since x is the number of times we increase it 25, we need to unincrease it. We need to decrease it 55 times, which gets you quite a bit less of a price. But you're going to get a whole lot more sales. Let's take a look at what the sales are. They're going to be doing 300 minus 5 times a negative 55. Well, they're going to increase their sales to 3,275. A lot more sales for a new revenue of looks like 1,653,125. Looking at a bunch more money here in the millions. Now, there is another consideration that I have to take in as you get more sophisticated in your mathematics. Maybe take a business calculus class. You'll learn that, it turns out that maximizing revenue is not really all there is to it, because you've also got to realize that you've now got to make all those carts. So if you're going to make that many carts, you got to have that many employees. You got to have that much space. And that can cut into your profits as well. And then it gets even more crazy when you start talking about quality control and blah, 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 blah. But we're on our way. You can see how that kind of works, right? All right, let's do another problem here. We've got watercolor. Okay, so another revenue problem. Give this one a try. Okay, watercolor paints nice pictures. These days, it seems everyone wants an authentic watercolor for their home or office. Right now, Walter can sell his wonderful paintings called Cats Playing Mahjong for $230. However, if he copies the painting, he can sell two of them and make more money. Unfortunately, since the paintings are no longer one of a kind, he would only be able to sell the two paintings for $225. Likewise, if he makes three paintings, he'll only be able to sell them for $220 each. How many copies should Walter make to maximize his revenue? So as a painter, Walter realizes that the price of the painting is going to go down as he reproduces it multiple times. So in this case, I would argue we couldn't go negative like we did in the last problem because you can't have a negative amount of paintings. So he's stuck at that 230 price. So let's take a look. So Walter's revenue is going to be equal to the price that he sells it at, which is 230, but it's going to go down $5 every time he copies it. But he's going to be able to sell one more for each one he makes. So originally, this is how it starts, right? The original price was 230. The original quantity was only one painting because everybody wants one, so he sells every one he makes, right? Then as he decreases the price by $5 by copying it, he then gets to sell one more at X. And so let's graph that and see where that ends up putting us. 230 minus 5x times 1 plus x. Okay. Again, I'll go back to just a standard view here. Always a good idea to do that first. Okay, well, that would be if he sells 40. So if he makes 46 copies, he has to just give them away, right? Yeah, this is taking me a while to get up there. Let me go to the settings here. I'll say let's say 0 to 50. And I'll look at my revenue going from 0 up to, let's say 2,000. Is that going to be enough? Nope, it's not. I like how you can see the graph behind you while you do it. It's kind of nice. There it is. So 22 and a half. So really he needs to copy it about 22 times. He could also do 23 times probably to keep the customers happy. He's going to get the same amount of money because it's actually half a copy you should do. So how many copies should he make? 22 or 23 copy. Well, actually, let's think about it. Yeah, those are the copies because we got the one original, but you should make that many more copies. All right, let's go to the next one. Reminiscent. Give this one a try. Okay, hopefully you had success with this one. Reminiscent has an old 8 by 12 inch black and white photo of his childhood home. He wants to put a uniform width border around the photo before framing it. Remy decides that he wants to make the combined area of the photo and border to be twice the area of the photo alone. How wide should Remy make his border? So it's an 8 by 12, right? So we know that area is length times width. So the area of the photo is equal to 96. But he wants to make that double. So he wants to double this, which would give me what? 192. That's going to be the new combined area, right? So the amount that he's going to add is going to be look for this word, he wants to put a uniform border, right? So that means it's going to be X wide and X tall, okay? Whoops, mine doesn't really look very uniform, but you get the idea. So my new area is going to be 8 plus X and 12 plus. Well, whoops, I just made a big mistake. Did you catch it? Because guess what? When we add that new area, it's not going to be just X in this direction. It's also going to be X in this direction. So actually, I'm going to be adding X twice. I'll be adding it once on top and bottom, and then once on left and once on right. So we have to do X all the way across on both sides. X, X, and then this here was the 8, and then this is X, 12, and then another X. All right. Sorry if that got confusing there. I'll go back to just the previous picture there. All right, so we have to do 2x, and then this has to be 12 plus 2x. And this time they're just asking when does it equal the combined 192. So this would be a pretty easy problem for us to just multiply out and solve with a quadratic formula. But let's use a graphing calculator since we've been doing that. Let's see how I can do that. I'm going to say 8 plus 2x times 12 plus 2x. And I'm looking for when this equals 192. So I will change my settings to make it go up to like 300 maybe. Looking for 192 here. Well, it looks like it's somewhere around, well, maybe around 2. Oh, look, it's exact. If it wasn't, you're allowed to graph just a number in decimals like that, and you can then click on it and get the answer. 2 and 192. So it turns out that the x value of 2, so how wide should we make it? We're going to make it a 2-inch wide border. Isn't that amazing that just adding a 2-inch wide border would actually like double all the sides? Which is weird, right? That should just be that, right? I always spell border wrong. Anyway, I think that's it for this lesson. So take care.